In this segment, we will find the transverse compressive strength of a unidirectional lamina. First, we will model how we can find the compressive strength. Next, we will do an example, and after that, we will see that how we find this particular value experimentally as well. So far as modeling the problem is concerned, it's exactly the same as we model the transverse tensile strength of the unidirectional lamina. So the only thing which you have to recognize is that this is what we got as the formulas for our ultimate tensile strength in for the transverse direction. The only thing which we are doing now here is that the ultimate tensile strain in direction 2 is replaced by the ultimate compressive strain in direction 2. And here, rather than using the ultimate tensile strain the matrix can take, now we are substituting by the ultimate compressive strain the matrix can take. So that's the only difference. If you want to look at the full derivation, just go to the video which is on the transverse tensile strength formula, and you'll be able to get that. And that's also in the description of this YouTube video. Let's go through the example. We're given a glass epoxy lamina with 60% fiber volume fraction. The fibers are circular and a square array. And we're given the modulus of the fiber in the matrix. We're given the Poisson's ratio of the fiber in the matrix. We're given the ultimate strength of the fiber, ultimate strength of the matrix. And keep in mind, this is a compressive strength of the matrix here. Epoxy does have a higher compressive strength than the tensile strength. So we are reporting here the compressive strength of the matrix, the epoxy. And what we want to do is we want to find the ultimate transverse compressive strength of the unidirectional lamina. So we follow the same procedure as for the transverse tensile strength. So here is the formula for it. And the reason why I'm writing the formula is so that we can identify what we need to find before we put any numbers in the formula. So we first got to find out the Young's modulus in direction 2, the transverse Young's modulus. We got to find the D by S ratio, that's the ratio between the diameter of the fiber and the spacing between the fibers. And we got to find out what the ultimate compressive strain in the matrix is. So let's go and find one at a time. What's E2? We'll use the reciprocal formula here. And we have this. The volume fraction of the fibers is 0.6. The Young's modulus of the fiber is 85 gigapascals. The volume fraction of the matrix is 0.4 because it'll be 1 minus 0.6. And the Young's modulus of the matrix is 3 gigapascals. And that gives us the value of E2 as 7.123 times 10 to the power 9 pascals. If we want to find out the diameter to the spacing ratio, since we have circular fibers and they're in a square array, that's the formula for the D by S ratio. So that gives us 0.6 divided by pi, and that gives us this value was 0.8740. So we have to find one more value, which is the ultimate strain the matrix can take in compression. Let's go and do that. So we have epsilon MC ultimate will be equal to whatever is the ultimate stress the matrix can take and divided by the Young's modulus of the matrix. This is given to us as 100 megapascals, the ultimate strength of the matrix in compression. Young's modulus of the matrix is given to us as 3 gigapascals, and that gives us a value of strain as 0.0333. So going back to our formula for the sigma 2c ultimate, we will get the Young's modulus in direction 2, or the transverse Young's modulus, which is 7.123 gigapascals. Then our D by S ratio. Then the Young's modulus of the matrix, Young's modulus of the fiber, plus 1 minus the D by S ratio again. And this whole thing multiplied by the ultimate strain in the matrix in compression, which we just found out to be this value. So once we do all of that, we get 3.723 times 10 to the power 7 pascals, which is basically 37.23 megapascals. Let's go and see that how do we experimentally find the ultimate compressive strength in direction 2, or the transverse compressive strength. So what you're seeing here is the transverse compressive strength specimen. It is exactly the same kind of specifications for the specimen. Length is given as half an inch, which is exposed, and the rest of it is in the vices in the iterary fixture. The difference which you are seeing here is that we're using higher width. Generally, in the longitudinal compressive strength specimen, you'll find about quarter of an inch. Now here you're seeing half an inch. That's again so that you can have higher buckling load, so that when you are compressing it, that it doesn't buckle. We are still using the ASTM 3410 standard, which is the iterary, with the iterary fixture. And in the 0-degree ply or the longitudinal compressive strength test, we use 16 to 20 plies. So that's what was used for the 0-degree plies. But here now we're going to use 30 to 40 plies when we have 9-degree plies. Again, because we're using a thicker laminate here, because we don't want it to buckle, so that it can take higher load before it buckles. These are some of the test results which you're seeing here. We are plotting the transverse compressive stress as a function of transverse compressive strain. So all you're doing is putting a strain gauge perpendicular to the fibers and being able to calculate that. Now you can take the initial slope of this one, which will give you the transverse Young's modulus in compression. So that's given as 93 gigapascals. You will find out, hey, this is where it takes, that's the maximum stress which it can take, that's 198 megapascals, and this is the maximum normal strain which can take place in compression in direction 2, and that's 2.7%. And as you can see here, that we're using 40 plies as opposed to 16 to 20 when we are doing the longitudinal compressive test. And that's the end of this segment.